Yeah, so welcome back to the third day of our Geometry and Tacos discussion on LCK and Weissman geometry. So we're very happy to have Liviu Ornea from University of Bucharest again talking to us, this time about some more recent research. So please, Liviu, just take it away.
Thanks, and thanks for inviting me and for giving me the opportunity to talk about things I like. I apologize for Monday talks. They weren't well calibrated. Hope to be better today. So I'd like to talk about some rather recent results together with Misha about different kind of bimeromorphic properties of these manifolds. There are mainly three results. Two of them are related. So let me first start with, I don't know, you see the whole slide because I don't.
Yes, I think it's all there.
Okay. I'll first recall what was the beginning of the business, because our first result will be about a minimal model in LCK geometry. So everything started in 1901 with Castelnuovo. It was the big period of Italian algebraic geometry school. They were all projective guys. And Castelnuovo had this criterion for birational contractions of projective surfaces. Then projective surface was called minimal when it cannot be contracted. So when it is not blow up, for example. And then together with Enriquez, in the next almost 20 years, they gave a rather complete classification of projective minimal surfaces. And then in the 50s, Kodaira extended their results in the analytic category to compact complex surfaces and showed that many or most of the results known in birational geometry hold good for complex compact surfaces. Finally, Mori generalized Castelnuovo Enriquez this minimal modal theory to higher dimensions. It was a program, and it is ongoing. One of the latest findings is Höring-Peternel for Kähler manifolds for three folds. So when we say minimal modal, we are thinking about algebraic geometry or about Kähler manifolds in any case. For non-Kähler, it's the notion which is correspondent to birational is the bimeromorphic geometry. And for non-Kähler manifolds, not much is known. There are, of course, several important results for balance metrics. I shall review them. And recently for LCK manifolds. So, of course, this is what I want to talk today about LCK manifolds mainly, but also about balance. So, as a preparation, let me recall that the blow-up at points of an LCK manifold preserves the class. This was a result stated and proven with the flow by Tricheri. The flow was corrected by Vuletescu many years ago. If I have time, I'll tell you the story. And then the three of us, we solved the blow up along compact subvarieties and the blow down. So the condition is that when you blow up along a subvariety, that subvariety has to have an induced Kähler structure. That is, the Lie form of your LCK manifold should restrict to an exact form on the submanifold. So the difference is important when you have a curve, because a curve is itself a Kähler, but you don't care about its intrinsic Kähler metric. You want it to be induced Kähler. So this is the situation for the blowups. And as an obvious corollary, the blowup of a Weissman manifold along a submanifold is not cannot be LCK. This, if you remember, is because of the existence of the canonical foliation, which I call sigma. So the canonical foliation eats all complex submanifolds. So complex submanifold is Weissman, or it is an elliptic curve. So a leaf of the canonical foliation. And in first case, you see the leaf form cannot be exact because it's a Weissman submanifold. And in the second case, being a curve, the leaf form is constant on the leaf. Okay, now this business of blow up, the fact that the blow up doesn't behave well on LCK manifolds, unlike the Kähler case where it behaves very well by Blanchard, was corrected somehow by Angela Parton and Vuletescu in their work on algebraic dimension, LCK with fixed algebraic dimension. So they introduced this notion of weak locally conformally Kähler structure. And this is a weakening, of course, of the definition. You have the tensorial definition, but omega, you don't want it to be strictly positive everywhere, but only outside a proper analytic subset. You see that this idea of introducing a proper analytic subset and neglecting the outside is exactly what happens when you study meromorphic functions and bimeromorphic transformations. So their theorem is that a proper modification admits weak LCK structure. So this property is preserved by modification. And they, of course, they extend the Weissman theorem. They use this notion to classify up to bimeromorphisms LCK manifolds of dimension 3 and algebraic dimension, maximum algebraic dimension, but not Moishe-Zon. And we have a work in progress now, but it is not finished and not everything is proved. But I think we can prove this result that which generalizes, extends theirs. That dimension n with algebraic dimension n minus 1 should be Weissman. But it's still in big progress, let's say like this. Okay. There's this notion of Fujiki class C that is, of course, very important in Kähler geometry and in birational, in bimeromorphic geometry of Kähler manifolds. is defined as the class of complex manifolds bimeromorphic to Kähler. And of course, it contains the Moishe-Zon manifolds, which are not projective. They are bimeromorphic to projective. And it is known that these manifolds satisfy DDC lemmas. Usually, here is where we look for non-Kähler manifolds satisfying the DDC lemma. From the work by Angela Ugarte, we can derive this simple result that Moishe-Zon manifolds do not admit LCK metrics which are not of Kähler type. That's the Fujiki class C in Kähler geometry. We want to pass to LCK manifolds with an analog. So to this end, we recall that Kähler current is 1-1 current, it's closed and has this kind of positivity. So the condition of positivity is to be greater than some Hermitian, smooth Hermitian form. You don't need closeness of this Hermitian form. You need the fact that it is positive, this Hermitian. And there is this big result of Dumailly and Paun that Fujiki class C is characterized by the existence of Kähler currents. And this is the way in which you can move to LCK, because now you can extend this notion to and call it LCK current. You want it to you fix a closed real one form, and then you have you want this. The notion of positiveness is the one that we gave here. Then you want it to satisfy also this property. So these are the LCK currents, and rather recently, say, Shimobe extended this theory to LCK setting. It's a paper in Geometria Dedicata in 2018. So in dimensional list 3, if you have a submanifold of codimension at least 2, then finally the blow up of a compact Weismann manifold along such submanifold does not admit any LCK current. It tells you how to do the blow down also. Moreover, defining the LCK class C or LCK Fujiki class C as the set of the class of manifolds bimeromorphic to LCK, Shimobe proved that this class can be characterized in an analogous manner with the Kähler Fujiki class C. He also proved something nice again as Alexandra did for Alexandra with her co-authors did for Kato. Shimobe used standard Hironaka construction and showed that there exists a modification of an LCK manifold without LCK metrics. And he showed that it admits locally conformally balanced. And this, as I shall recall, is a parallel to Alessandrini-Bassanelli result showing that the modification of Kähler doesn't admit necessarily that was known Kähler matrix, but it admits balance matrix. Moreover, you see that the Maipon characterization doesn't hold for LCK Fujiki class C, so it's not bijection between the existence of currents and bimeromorphisms. So this is the general picture about LCK in general and about behavior to bimeromorphisms. Now, a first result that we had in this regard, in this respect, is a striking and unexpected for us, at least, unexpected feature that the minimal model, if it existed, unique in the LCK class. So the exact statement is this one: you have a compact LCK with exact Kähler form on the minimal cover. And then you can show that any bimeromorphism 2M is holomorphic. I mean by this that it is a true map, not only defined on an open dense set. It is a true map and it is holomorphic, not only meromorphic. This is not, it wasn't expected, I think. And it applies to two very different kinds of LCK manifolds, to LCK with potential and to OT. They are completely different, not related. But as I stressed in my previous talk, they both have exact Kähler form on the covering, with the difference that the potential in the first case is automorphic, and for OT manifolds, the potential is not automorphic. As you shall see in the proof that I want to present, in fact, we don't use, not even in the LCK with potential case, the automorphicity. So this is why we stated like this the result. And of course, it can be, by the proof, we shall see that we could formulate it for Kähler manifolds like this. Only we didn't formulate it like this. We just put it in the end as a small remark, because we expected that Kähler people would be completely not interested. They will say that it's clear, it could be guessed or something. It's difficult to shock Kähler people with things like this. So we stick to our LCK setting. And I'd like to give you the proof of this result, because it's nice and it's not very complicated. So I can spare a little bit of time with it. You start with the graph of phi, because the very notion of bimeromorphism means that the graph has some properties. Of course, by graph, you know, phi is defined, is in fact a phi sub u, which is defined on an open dense u. And when I say the graph of phi, it is the graph of this phi u closed in the product. So I take the closure of the graph of where the phi is really defined. So this is my x. and it projects to M and M1 from the product. It's a complex subvariety. These are bijections in a general point. So from the proposition that I quote here, we see that it will be enough to show that the preimage of a point, of a general point, from M to X to the graph is finite for all Z, sorry, not for M, from M1, the target. M1 is the target. Because the target is smooth, and hence it is normal. I use the normality as in analytic category. Bounded meromorphic functions and open sets are holomorphic. And we have this proposition that, which proof I postpone. If we have a normal variety and a holomorphic map, closed holomorphic map to it, such that the fibers are finite for all Z and bijective in a general point, then it is biholomorphic. And this proposition follows from general theory. So I won't prove it, I just use it. And hence, now all that matters is to prove that this fiber is finite for all Z. Okay? Sigma 1 is the projection, which is bijection, from the graph to the target. Let's see. And the reasoning is by absurd. So suppose the fiber is positive dimensional. Of course, the projection is bijective on each slice in M. And hence, Z1, this fiber, projects to M holomorphically and bijectively. So, see, I started by looking at this arrow, and now I move here the discussion. And I call Z the projection. This is some submanifold, some subvariety in M. But because this property by Remark, Z is a complex subvariety. It's not only a space, it's a complex subvariety. And now let me assume this strange property that pi1 of Z viewed in pi1 of M contains an infinite order cyclic subgroup. And I shall prove it. But for the moment, let's assume it. Okay? You have Z included in M, so you have a map between the fundamental groups. You take the image of it, and you make this assumption. Then its image in pi1 of X, because M is included in the graph and is the same, also contains an infinite order cyclic subgroup. But this is impossible because you have this equality and also pi1 of M1 because you have a bimeromorphism, and the projection of Z to M1 is only a point. So this is the contradiction, and we remain to prove the existence of this infinite order cyclic subgroup. That's the precise statement. You have now you forget bimeromorphicity and everything. So you have a compact LCK manifold. You have its scalar cover with deck group Z. You have with deck group gamma. You have a subvariety of positive dimension. And now you use finally the fact that the Kähler form is exact. This will ensure that pi1 of Z and pi1 of M contains an infinite cyclic subgroup. Here's how. You pass to the cover of Z, which stays in M tilde. And if pi1 of Z and pi1 of M is finite, then of course the cover is compact. But this is impossible because omega is exact. That's all. Similarly, this restriction is not a pullback of a Kähler form on Z because you are in LCK. Then gamma acts by non-trivial homostasties. Hence, the character is non-trivial. But if it is non-trivial, take an element whose image is different from one, and this will have infinite order. So its image in pi1 of M has infinite order, and that's the contradiction. So we only use the exactness to know that Z tilde is compact. Okay, that was the first result, which I think it's nice and interesting in itself, but we shall use it in the second main result that I have, and which regards balance metrics. We call them balanced. Any questions so far? I don't hear anything, so I presume I can go on. I don't see faces. So I see only my slide. So maybe from time to time someone tells me that it's okay.
Yeah, I think we're good for you to continue.
Okay. So let me just recall that balance metrics, which are defined as you know, d omega n minus 1 equals 0, n is the dimension. We call them we call them balanced since the paper by Michelson in 82, but they were in fact introduced by Paul Gauduchon in 77 as semi-Kähler. He claims that they appear like that I think in the book about connections of Lichnerovich, but in fact, the one who introduced them properly and studied them is Gauduchon in this beautiful paper about bundles with semi-positive Ricci curvature. 77. No one cites him. You know that balance metric exists on all twistor spaces. This was proven by Hitchin for 4 manifolds and by Paul Gauduchon on conformally flat Riemannian manifolds. He also proved that these twistor spaces are Kähler if and only if the base is CP2 or S4. And the breakthrough was this paper of Alessandrini Bassanelli when they showed this property, that balance property is Bimeromorphic invariant. And that made balanced metrics so important. They also exist on all Moishezon manifolds, and more generally on Fujiki class C manifolds, as we saw already. So, as I already recalled, the Kähler property is not bimeromorphic invariant. However, modifications of Kähler admit balanced metrics, and modification of LCK admits locally conformally balanced metric. Now, concerning the relation between balanced and LCK, there is an old result by Alexandrov and Ivanov that the Hermitian metric on a compact complex manifold cannot be simultaneously balanced at LCK. That's not so difficult to prove. And after that, other results appeared that LCK is not compatible with a same metric, cannot be in the same time LCK and pluriclosed, for example, or LCK and I don't know, strongly Gaudichon. But the problem is if there can be on the same complex compact manifold different metrics with with these properties. So the conjecture is that in dimension at least 3, there cannot be both LCK and balanced different metrics. We don't know how to prove it in full generality. But it was confirmed for nil manifolds, two-step nil manifolds, for example, by the paper with Alexandra and Miron. And now we prove this theorem with Misha. This is the second main result I want to talk about. That the conjecture is true for the known LCK manifolds. So we cannot prove it in general for the LCK class, but we can make an analysis case by case for these classes. OTs, LCK with potential, which you remember include Weissman, and for Kato. And as far as we know, this is the best result that we can have at the moment. Now, I'd like to postpone the proof to be sure that I can make other comments. And if time permits, I'll give the proof or at least sketch it because it is rather involved. So let me first make some comments about the statement and kind of idea of proof. I'd like to recall the notion of degree. It is a degree that we all know how to build using Gaudichon's forms. So let's look at this natural map, going from the first cohomology, Durham cohomology, in Botchern 1-1. It was already used plainly yesterday, so you know very well what it is. So it is clear that if you take a closed form, then DC of it will be Botchern closed. This is seen in this simple computation. So DC alpha is D of I alpha, and it is exactly D alpha 1, 0 modular constant. So you have this natural map. And if we fix a Gaudichon form, that is a form which just satisfies DDC omega n minus 1 is 0, I can define the degree of alpha. It is the same as if I say the degree of the form alpha or the degree of the class, because it is invariant on the class, as this integral omega n minus 1 wedge DC alpha. The fact that DC alpha is exact tells you that the integral is well defined. And you see it is a functional on H1. Okay, so far so good. We have the notion of degree. Now, a third theorem that we could prove is the following. Apparently, it doesn't have anything to do with the first one, with balance, but you will see. So I take a compact LCK manifold, which is of non-Kähler type, and as usual, I impose this condition of the on the dimension. And if M is bimeromorphic to either LCK with potential, Earlier-Claus-Thoma or Kato, that is, it is bimeromorphic to one of the known LCK manifolds, then the degree of the Lie form is strictly positive for any Gauduchon form, not only for omega, for any Gauduchon form. And this is the statement which is related to the title of the talk, because the theorem, what I call theorem B, about the existence of balanced and LCK metrics, doesn't seem related. However, from theorem C, we can derive easily theorem B. Because if M theta is bimeromorphic with this, with one of the known manifolds, LCK manifolds, and the degree is strictly positive for all Gauduchon forms, and we suppose that there exists also a balanced Hermitian form on M, then we compute. This is strictly positive. However, d theta closed implies exactness of d theta, dc theta, as I showed, and this is a contradiction. So it's trivial. It's a trivial implication of the theorem C. So the real theorem is this one, which regards the bimeromorphic category. And so the proof will be for theorem C, not for the LCK versus balanced. Now, I'd like to explain a bit what stays behind that theorem. It is this conjecture that we cannot prove for the moment, that the degree is strictly positive for any Gauduchon form on any LCK compact manifold. We know how to prove it, as you saw, for manifolds bimeromorphic to the known ones, but not for any. And of course, the difficulty lies in this for any, because for the LCK form, it is very easy to compute. It's a direct computation. Now, let me explain more the meaning of this conjecture. We need to recall the notion of pseudo-effective elements in the Botchan cohomology. We call such an element pseudo-effective if it is the class of a positive closed 1-1 current. You remember what the closeness of a 1-1 current is. It has to be strictly bigger than a Hermitian form. And then you can look at the pseudo-effective cone, which is formed by, it is a cone, all the classes of pseudo-effective currents. There is also a second cone, which is called Gauduchon cone of classes of Gauduchon forms, but classes of omega already taken at the necessary power. And this is a cone which stays in Apli cohomology, which is the dual of Botchan. And this is a celebrated theorem on Lamarie, which was also considered by Popovic and Ugarte in 2018, that It characterizes the bot churn, the pseudo-effective cone. It is the dual of the Gaudichon cone. That's what is saying. And the duality is expressed by evaluating pseudo-effective bot churn class on Gaudichon forms. This gives the duality. And hence, an equivalent conjecture with what I said here is that the Botchan class of DC theta is always pseudo-effective. This is what we claim. On the other hand, I think at the end of the talk of Monday, I discussed the set of Lie classes of an LCK manifold. It is a subset in H1 in the Durham cohomology. All the classes which representatives can be Lie forms for some LCK metrics. And for LCK with potential, this L is an open half space. I didn't give the proof. It was known before us. It was known for Weissman, that Tsukada proved it for Weissman. I didn't give the proof of this, but if one examines the proof, sees that, in fact, what we proved is that this Lie cone is the set of all alphas such that the degree is strictly positive for a Gaudichon form. It was defined like this, in fact, this half space. And hence, what our conjecture claims is that at least half of the characterization holds on all LCK manifolds. So it is a statement about the Lie cone. And again, postponing the proof of the main theorem, which was theorem C about the degree, I'd like to give you also another bimeromorphic object, another object which is invariant to bimeromorphisms on LCK manifold, which is related with these cones, and that we called the Lie-Gaudichon cone. It can be defined on a Hermitian manifold in general. And it is the set of cohomology classes, Durham cohomology classes of degree 2n minus 1, such that this integral alpha wedge rho vanishes for all closed holomorphic forms of type 1, 0, obviously. On Kähler manifolds and on Fujiki class C manifolds, this integral doesn't give anything, so the Lie-Gaudichon cone is trivial. So it is interesting on manifolds which don't satisfy the DDC lemma. And what we proved is that it stays constant under bimeromorphisms. So it is another bimeromorphic invariant associated to, in general, to complex manifolds, not only to LCK, but we could compute it for the known classes of LCK manifolds. Can be, and we did it. It's rather interesting, but for the moment we don't have many applications. Now I have 5 minutes left. I'll try to pass just very quickly through the proof of CRMC. I recall CRMC was that the degree of the Lie form with respect to any Gaudichon form is strictly positive on all LCK manifolds which are bimeromorphic to either LCK with potential, early claustoma, or Kato. There are 3 or 4 steps, and some are technical. So first of all, the result is true on OT, because there we have a formula for DC theta. If you remember, it was this formula DC theta is omega minus theta wedge theta C, which is the same also on LCK with potential, and is known to be positive. And using the minimal model, the uniqueness of the minimal model, bimeromorphic and bimeromorphic manifolds to Weissman or T are blow-ups of Weissman or T. And this positivity stays. The pullback of positive forms is positive with respect to blow-up.
Liviu, could I ask a question here?
I'm sorry?
Could I ask a question?
Please.
Yes. So the fact that DC theta is positive is pretty clear for if you actually have a Weissman metric you're working with, or the LCK metric that you construct directly for the OT manifolds. This is true just for any LCK metric on a Weissman manifold or an OT manifold?
Yes, for the Weissman manifold, it is always true, because or on Weissman, you have that formula that I recall. DC theta is omega minus theta wedge theta C.
So that's true for the Weissman metric.
Yes.
But for a
for the
non-Weissman...
OT, you have, for the OT, there is only one class of the LCK metrics.
Okay.
Of the Lie form. There is only one class.
Okay. And then on
that's the feature
manifolds...
of Inoue and OT. The Lie cone is a singleton.
Okay, sure. And okay, thank you.
Okay, so the pullback is will be positive. We know Weissman and OT is okay. Now, to pass to Kato or to Kato, for example, you use the characterization of Kato manifold as modifications of Hopf. And so you want to look at a smooth family of a deformation, smooth family of LCK manifolds, such that the statement is true out of the central fiber. And you fix a Gaudichon metric on the central fiber. You extend it to a smooth family of Gaudichon metrics. And this is possible because you look at the proof of Gaudichon, and you see that the existence proof, the proof of the existence of a Gaudichon metric, is proving that a certain elliptic operator has solution. And the solution depends continuously, smoothly on the initial data. Now, you use this. You extend your Hermitian form on the central fiber to a family of Hermitian forms. You take the Gaudichon metric of each of this Hermitian form. It depended smoothly on the initial data. So you find, if you suppose the statement is true on all fibers not central, you have this degree positive outside the central fiber, and hence, by continuity, you have the same result on the central fiber, but you still need to prove that the inequality is strict. And this is, now it will be to be proven. How do you use this result? LCK with potential are deformations of Weissman. Kato are deformations of Hopf, which are still LCK with potential. So it is enough. If you know this, if you knew the first step and this deformation argument, you have this inequality on all of them. Now the blown up Hopf is bimeromorphic to LCK with potential. So what you need to prove is the strict inequality. And this is by Lamary. In fact, it's a bit tricky because you know that this is theta is pseudo-effective, and then you represent it by a current. So you pass from forms to currents. So the class of this is theta, you look at it as the class of the current. And you integrate for some Hermitian form U, and Lamary tells you that if the integral is zero, that is, if the inequality is not strict, then theta is zero. So you don't have this result for forms, you have it for currents. But then if the current is zero, also the class of this is theta is zero. If the class of this is theta is zero, this theta is ddcf for some f. And then it is just a small computation. So this is the technical part. The trick was to pass from forms to currents and then to go back to forms. That's it. Thank you. I'll stop here.